All right, it's time to begin. It's Friday. We're going to start 3.1 today. Hey, how was that quiz on Thursday? What? Was it good? She pointed at me and said something. Okay. Yeah, that's a good strategy. Anytime your professor ever asks you, was that too hard? You always say, oh, we say, yes, it was difficult, but I think if we study hard enough, we can manage. But still, don't let the quizzes fool you. Don't let the homework distract you. The midterm will be hard, okay? I'm sorry, I'm not writing it, but I'm pretty sure it's going to be scary. And I'm not telling you that to scare you. I'm saying that when you get in there, you relax, you take a deep breath and said, okay, Bart told me this is going to be hard. I can do this. I'm going to make it. All right? Let's see. Aha. Last time we finished up the section on limits, right? Can somebody tell me what's the intermediate value theorem? What's that all about? It doesn't have to be precise. You don't have to be exactly right. I just kind of want to know the idea. What's up?
Pretty much if you have two functions that are
That's true. That's true. He says if you have two functions and the start point, this is my story from last time, but you really only need one function. Do you remember how it's explained it with one function? Yeah? So you have an interval, and you have a and b, and you want your function to be continuous on the interval. Okay, and so last time we subtracted the two functions, but here we have a and b, we have a function, it's continuous, right? And then what happens? Uh-huh. If at A it's bigger, right, and at B it's smaller, then there is a point C someplace. There is this point C where they somehow meet, and the function has to be continuous, right? Continuous function on an interval. How might you use the intermediate? By the way, what is what value, what intermediate value do you want it to hit usually? 0 usually. Okay, so this is a way that you can say a solution exists. Okay? The solution exists because the function is continuous and it's above the x-axis here and it's below the x-axis here. Therefore, by the intermediate value theorem, some root must exist. That's the idea. I just mentioned that again because the intermediate value theorem is something that's kind of complicated, and I want you guys to know it. All right. So, the bread and butter of Math 1151. The bread and butter is shoot. I'm going to have problems with my singular. Anyways, it's derivatives. Derivatives are what this class is really about, and that's what we'll talk about today. Okay. And last time I said, what is a tangent line? And I didn't preface it. Well, whatever. I said prepare to be wrong, and the answer that was given was the answer I expected. Was the answer that we usually give. Was a tangent line crosses the curve at one point, right? That's true for a circle. A tangent line does cross a circle. Look, would you guys agree? Well, I don't know what tangent means, but would you guys agree that this line is tangent to the circle? Yep, me too. And does it cross the circle at one point? Yep, no problem. The issue comes up when we have fancier curves. A curve like this. No. This line is tangent, and it crosses the curve many times. You see what I'm saying? Still tangent. So what's a better definition? Well, this is hard. This is really hard. This is not easy. A better definition might be a tangent line just touches the curve and goes in the direction of the curve, whatever that means. All right? That's one. If you go and you start reading about tangent lines, you might see something just like that. But here's my favorite informal definition of a tangent line. And by the way, part of the class is to give a better definition of tangent line. So the fact that it's a little bit hard for us at first, that's no big deal, because that's part of our goal. So here's the definition that I like. The Dr. Snapp endorsed definition of tangent line. You have your favorite curve. There we go. And to be tangent at, say, this point, what you do is you zoom in. You zoom in and you make a little box around this. And then we're going to zoom like this. See, here's my box that I'm zooming with. And when you zoom in, your curve looks like this sort of, right? Does that look like a nice zoomed in picture? And then we're going to zoom in again. Zoom in again until your curve looks like a line. The line that it looks like is the tangent line. I like this. What do you guys, does this kind of make sense? You're making a face, so is it okay? All right. Does this make sense to anybody back there? I can't see you as well. Thumbs up? Oh yeah, I like that. That's awesome. Okay. So the line that this thing looks like, and what I could do is I could even get more colors out here, get some green. I could say, well, this blue thing looks like a line, right? Looks like a line. There's the line that it looks like, and here's the line that it looks like, and then here is, there's the tangent line. Does that make, I like it. I like it. And I like this zooming in idea because I feel like the zooming in really says, hey, we're talking about limits. Limits are about looking at a function close up. I see the limits happening here. So this is the zooming. So what's a derivative? The derivative is a formula for the slope of the tangent line. The derivative is the formula for the slope of the tangent line. Okay, and now I'm going to ask you a conceptual question to see if you understand the concepts involved. This question is not hard. The question I'm about to ask you is very easy if you understand what's going on. And if you don't know what's going on, the question is practically impossible because you're like, I don't know what you're asking. Okay, so we'll see what happens. Here's my conceptual question. As far as I know, I made this question up. Y is equal to 7x minus 4. So here's a formula for a line, right? Line, great. This is a tangent line. Tangent, it's tangent to f of x at x equals 2. So you plug in 2, and this line's tangent to f of x. Find f of 2 and the derivative of f at 2. Yeah. So what's the derivative? The derivative is the rhymes with rope. Slope of the tangent line. So what's the derivative? So the slope of the tangent line at 2 is 7. So the derivative at 2 is 7, right? And what is f of 2? So the derivative is 7. Derivative is 7. I'm going to have to erase my beautiful picture here. That's why I was trying to avoid doing that. The derivative at 2 is 7. It's the slope of the tangent line, and the tangent line is 7x minus 4. What is f of 2? 10. How'd you get that? Yeah, and you know the tangent line is equal to the function, right? At 2. So f of 2 is equal to 10, which is 7 times 2 minus 4. Easy question, right? But there's some concepts going on, making sure you're understanding what's happening here. Okay, so now, let's see. We have some complicated symbols for the derivative that you might not have seen before, okay? So notation for the derivative. Here it is. If you have f of x, if that's your function, maybe your favorite notation will be this. F prime of x. And so that means you take the derivative. That means you find the slope of the tangent line for any value of x. It's the formula for the slope of the tangent line. This is the derivative. That's not so bad. And then we also have this notation. D over dx. Oh, and you put fx right here. Now this thing here looks like a fraction, right? It is not a fraction. This is one piece. It is a complicated one-piece thing. It does not come apart. It just always is d over dx, not the fraction. All right, does that make sense? Great. Don't do funny algebra with that. Who said that? Yep. Yeah, don't do funny algebra with it. We're going to learn a way that you can kind of do funny algebra with it, but I advise against it almost at all times. Okay? These are the same thing. They're the same thing. These are equal to each other. They're the same. They're just different ways of writing the same thing. Calculus was developed in the mid-1700s by two different people, Newton and Leibniz. Newton did it first, but didn't bother telling anybody about it. And then Leibniz did it later, and Newton accused him of plagiarism and spent the rest of his life trying to destroy Leibniz's career. After Leibniz died, Newton was thrilled that his rival was destroyed. However, Newton was not a nice man. Leibniz got the last laugh because Newton's calculus was understandable by essentially only Newton. And our calculus is much more like how Leibniz thought of it. Also, Leibniz was a cool guy. He was a Renaissance man. He didn't try to destroy anybody. That's good, okay? All right. So, what's the derivative? Wait, what's the conception? What's the derivative tell you? It's the formula for the slope of a tangent line, right? That's a formula for the slope of a tangent line. If you take the derivative of a function, you get another function out. All right? Formula for the slope of the tangent line. Now I'm going to give you some meaning behind it, because this is not some this is actually really applicable. Okay? And my favorite application of the derivative, I don't know why, it just is if you have something that gives position with respect to time. This is position. P prime of t, that's the derivative. That's the velocity with respect to time. Can you imagine, if you know a formula telling you position, knowing the velocity is something you want to know. This gives you the velocity. If v of t is the velocity, The change in velocity. Derivative, the slope is how fast the function is changing. The change in velocity, what's that called? Acceleration. V prime of t is acceleration. All right. Oh, and wait, p prime of t is velocity, so we could write p prime of t here. And I can take the derivative of the derivative. That's when you put 2 primes up here. So if you have a position, you take the derivative twice, you get the acceleration. Newton, he was known for physics too, right? This is why he invented calculus, to work on physics. Smart guy. Not nice, but smart. All right. So now, derivatives also allow us to approximate functions. So oftentimes in real life, you get a terrible function. You get some function for whatever behavior you want to, and you just can't deal with it. Not only can you not deal with it, a computer can't deal with it. What are you going to do? Well, I have some function, and I know it doesn't look bad, but its formula is terrible. Okay? And I want to know what this is. Well, maybe I can compute its derivative, and then I can do stuff around the function. And what type of, the derivative gives the slope of the tangent line, right? And the tangent line looks like the function near those points. And why do we study, does anybody know why we study lines so much in 7th grade and 6th grade and 8th grade and 9th grade? Why do we study lines so much? Because they're easy. Lines are easy. You can always solve where lines equal x. Lines are great, super easy. Other functions, super hard. So derivatives allow us to approximate. Okay, and sometimes it's even called linear approximation. In a similar way, derivatives, as we're going to learn, I hope, I haven't actually looked, but I think we will, as we should learn, derivatives allow us to solve equations numerically. Will that we really have no business solving. They're too tough. My first job was in Myrtle Beach, South Carolina. I was at a small school down there. And a steel mill in Georgetown, about 45 minutes away, called me up one day and said, "We have a geometry problem for you." I said, "Okay, what is this?" And after talking to them, I figured out they had a robotic arm. It was like this, like, and they had a laser mounted on the one end. And what they wanted to do is they had this, the steel mill had this like Play-Doh Fun Factory version of steel, right? Where they shove the steel out like this. And they wanted to shine the laser at the end of the steel coming out and figure out how far it'd come out, moving the laser like, okay, right? Make sense? The only problem was you have to constantly, as the steel's coming out, you have to redirect the robotic arm, right? This is called the inverse kinematic problem. Basically what that means is, if you want to build a robotic arm, and I want to, here's some chalk, I have a robotic arm, and I want to pick up the chalk, how do I tell the computer to pick up the chalk here? You know, like how, I know I want to get here eventually, and coming back is easy, but going there is hard. We probably do it by some sort of approximation. We use our eyeballs and have muscle memory or something like this. But a machine can't do that. So I had to solve a terrible equation. Moreover, I had to teach them to solve, the people working on this, to solve the terrible equation. And so we used a method from calculus, and hopefully we'll learn it, and basically involves just taking the derivative and making some guesses, and you get very, very, very close. It was a neat application. All right? Okay, and economics. Economics, marginal. The word marginal means take the derivative. So the marginal cost is the change in the cost. The marginal demand is the change in demand over time. what's happening to the marginal demand of iPods? Yeah, well, you know, it's going, goes up, it went up, right? But do you think, are people still buying iPods? Why not? What's killing the iPod? Phones rock, you know? Cell phones rock. You know what cell phone really rocks? The Nexus 4. Maybe I'm not allowed to advertise things. I don't know. Forget that. Okay. Anyways, so the iPod, the demand for the iPod looked like this. You know, it started off and it was like, woo, and now it's kind of trailing off, right? And it started off, the derivative was huge, and now it's still trailing off. Does that make sense? I think so. Oh, marginal cost. That's a change in cost for production. Does anybody know what economy of scale is? Economy of scale. Here, I'll give you a hint. All these universities, they buy like, like 27 Xboxes, and then they like tape them together and make a supercomputer, and it's super cheap. I know an Xbox seems expensive, but you know, compared to a real supercomputer, it's not. Why can they build a better supercomputer by like buying all these Xboxes and taping them together than just building one from scratch? Why can they do that? Why are Xboxes so cheap? Because they're mass-produced, economy of scale. Okay, so to build one thing costs a ton of money. Okay, to build one thing, you know, to build one toilet seat for an airplane costs tons of money. Costs $10,000 because you have to make the machine that makes it, or something like this, right? But to make 1,000 of them, or not 1,000, 1,000,000 of them, you know, the production cost goes way down, because once you build one, you know how to, you just build all these. Is that marginal cost? So the marginal cost is the marginal cost. Let's see. I want is negative because the change in cost is going down. Does that make any sense? You don't have to understand all. I'm throwing a lot at you today. I'm just giving. Oh, what else are derivatives good for? Believe it or not, they're going to help us compute limits later on. Limits that we thought were terrible to compute, derivatives will be like, we can use some tricks with derivatives and we take care of the limits. That's fantastic. It's called L'Hopital's rule. L'Hopital's rule was written by Bernoulli, and L'Hopital stole it from him. L'Hopital said, I like that calculus thing, you know, Bernoulli. That's pretty awesome. And Bernoulli's like, yeah, it is. And he said, hey, if I pay you, will you come teach me calculus? And Bernoulli's like, sure. And so Bernoulli goes over and says, I'll teach you calculus. And L'Hopital's like, that's great. This is good stuff. This is good stuff. Takes his notes, takes it to the publisher. My calculus book. Now, I mean, I'm giving L'Hopital a hard time. But yeah, he did kind of copy Bernoulli's idea. Okay, so, but Bernoulli has lots of stuff. It's fine. Finally, derivatives are good because they help us optimize things. They help us be efficient. Optimization. O-P-T-I-M-I-O. There's an M-I-Z-A-T-I-O-N. Optimization, I think. That's when you make something really, you know, you want to minimize or maximize something. Like if you want to minimize the amount of gas your car uses. Here's how this would work. Here's how this would work. Okay, so we have a semi-truck. A semi-truck goes down the freeway, right? What's this? I can't draw very well, but I can draw a semi-truck. Here's what the front looks like. Am I right? Huh? Semi-trucks look like, look at this picture. I mean, seriously, folks. This is, bam! That's what a semi-truck looks like, okay? And what do you notice about the front of that semi-truck? It's not very aerodynamic, okay? So, as it goes faster and faster, what's going to affect it more? Air resistance, right? And so there's an optimal speed, because if it goes too fast, the air is pushing against it, right? And if it goes too slow, well, I can still go faster and get to my destination quicker and use less gas. There's an optimal speed for the truck to drive and save on gas. We could do a problem like this. I hope we do. Bart, watch this video and make this problem up for everybody. Check. All right. Past Bart, always 4 steps ahead of future Bart. Okay, so now, okay, so what's the definition of a derivative again? It's the formula for the slope of the tangent line. It's the formula for the slope of the tangent line. And last time we were talking about slope. Those mathematicians are always talking about slope. Okay, so, right, it's delta y over delta x, right? Change in y over change in x. It's all about change here. And this is equal to y2 minus y1 over x2 minus x1. This is slope. 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 We've learned this. I remember this from high school. And then this is equal to f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1, right? Slope. All right, and now, if x sub 2 equals x plus h, and x sub 1 equals x, right? That's okay. Then our derivative is, well, our slope is going to be this formula. F of x plus h minus f of x all over x plus h minus x. Do you guys see that? Look, this is the same formula. I'm just writing the same thing over and over again. Nothing has changed. This x sub 2 here is this x plus h. The f, there it is. And then the x sub 1 here is just this x. It's the same, it's the slope formula. You should be able to just write this down. It should make sense. You don't have to remember anything. It actually makes sense. And then what is x plus h minus x? H. So this is all equal to, these are all equal. F of x plus h minus f of x all over h. So this is a formula for slope. I think it's undeniable that's a formula for slope. And what's my favorite way of looking at to imagine what a tangent line is? I think of zoom, right? Zooming in. Zooming in. We're zooming in, and so we want h. We're trying to get these two numbers close together. They're close together when h is small. So the derivative, so d over dx of f of x, this is our derivative symbol, right? This is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. This is the limit definition of a derivative. I would bet money that you're going to have to use the limit definition of the derivative on the first exam. I would bet money that you're going to have to use the limit definition of the derivative on the final exam. Not much money, because I don't have any. Okay, but I would be sure that we're going to try to ask you something like this. I think this is going to happen. All right, I'm going to ask, what questions do you have? All right, I have another conceptual question for us. And then we'll start doing some examples. We're going to do 3.1 again on, if I read my calendar correctly, which, you know, I should check. Yeah, we're still on 3.1. That's how important 3.1 is. We're still on that on Monday. So we're going to keep on talking about this. Here's my conceptual question. If f of 3 equals 6, and f of 3.1 equals 6.4, estimate f prime of 3. Estimate f prime of 3. Is this a hard question? Yes? No? Maybe? I don't know. I don't know. We're going to watch you do it, Bart. And if you can't do it, then it's pretty hard. And if you can, well, maybe. I don't know. Okay. What do we do here? How do we compute f prime? Yeah. Uh-huh. Uh-huh. Yeah, so what we're going to do is we're going to, he says, make this fraction, Bart. You're going to make this fraction. We don't have any h's around, so he goes f of 3.1 minus f3 goes in for h, right? And then this is going to be f of 3.1 minus f of 3. You just write down this fraction, right? Cool. And what is f of 3.1? It's 6.4, so that's 6.4. Minus f of 3 is 6 all over 3.1 minus 3, that's 0.1. And so this is equal to 0.4 divided by 0.1. And what's that equal to? 4. So f prime of 3 is approximately 4. If you don't know what the limit definition is, this problem seems impossible because I don't give you enough information to solve it unless you know the limit definition, right? Let's do another conceptual problem. All right, here we go. This is a good one. Another conceptual problem. If f of minus 2 equals 4, if f of minus 2 equals 4, and f of minus 2 plus h equals h plus 2 squared, compute f prime of minus 2. Yeah? Exactly. So, yeah. So exactly. He says, hey, you're going to do is you're going to write the limit as h goes to 0 of f of minus 2 plus h minus f of minus 2 all over h, right? Right? He said minus 2, what you said, minus 2 plus h minus minus 2. But yeah, that's still h. And then that's going to equal the limit as h goes to 0 of, let's see, it's still going to be h down here, but I know that this is h plus 2 squared minus 4. And now we have a limit to compute. How do we compute this limit? What do we do? First thing we try to do is plug in, right? It's not going to work because in the denominator we get 0, and in the numerator we get 0 as well. So what do we do? What's that? Distribute the top, expand the top. That's exactly right. Just do this thing, limit as h goes to 0. And this is going to be h squared plus 4h plus 4 minus 4 all over h. And now what happens? Some 4's, the 4's cancel out. These two 4's cancel out. And I'm going to cancel out the h's a little slower, but yeah, they will. So let's see. So this is equal to the limit as h goes to 0 of something over h. So it's going to be h squared plus 4h. Aha! And now I can cancel an h because there's an h in every single term. And so this is equal to the limit as h goes to 0 of no fraction anymore, h plus 4. And now I can plug in 0, right? And so I see this is just equal to 4. So what is f prime of minus 2? 4. I'll write it down. Yeah?
How would you cancel out the 2's to just get 8?
Let's find out. Okay, so how did I cancel out the 2's to just get, oh, down here? Okay, so yeah, just to get this. Let's see what happens here. I'll slow it down a little bit. Let's see, this is minus 2 plus h minus negative 2 like this, right? Okay, so that's good. I'm going to write the next step just for completeness sake. 0. And then I have the same numerator, minus f of minus 2. And then this becomes a plus 2. So then we're going to have that. Is that okay? The minus minus becomes a plus, plus. Okay. What questions do you guys have about this? This is a hard question, kind of strange question, but not too bad, I don't think. This one's more, the next one is a little bit more common. Here it is. If f prime of x is equal to x cubed, if f prime of x is equal to x cubed, f of 1 is equal to 2, approximate f of 1.2. Any thoughts here on what we need to do? He says, take the definition and work backwards. That's a great idea. And in fact, I think it will get you the right answer. Okay, I really do. We can try, let's try that. That's not what I had in, when I wrote this problem, that's not what I had in mind, but you're the second person to do that, okay, that I've seen. And it's a very natural thing to do. He says, take the definition and work backwards. And so what he wants to do is this. He wants to say, okay, so I have the limit of, well, what you're going to write is, the definition is this. It's going to be f of, we don't know what f of 1.2 is, so we're going to have f of 1.2 minus, what's f of 1? 2 all over 0.2, then you say this is going to equal, what's it going to equal here? X cubed, but where are we at? We're taking the tangent line at x equals 1. That's a good, I mean, you're one or the other, right? At x equals 1, and so this is going to equal 1, because you plug 1 in. The derivative gives the formula for all the slopes of the tangent lines, no matter where you are. Right? Aha! And so look at this. Well, can we solve for f of 1.2? Heck yeah! Okay, so let's see. This is going to be f of 1.2 minus 2 is equal to 0.2. F of 1.2 is equal to 2.2. There we go. Or, sorry, not equal, but respect the equal signs. I should say approximately. These should all be approximately, I'm sorry. And why are they approximately? Why is it not equal? Yeah? Yeah, it's not really, it's just close. We're basically setting h to be 0.2 as opposed to taking the limit as it goes to 0. All right? Yeah, and that's a fine way to solve the problem. Is it okay? I'll just try to explain it more. That's all I'm going to do. Yeah, of course. Okay, so he says, use the definition of the derivative. So the definition of the derivative is this. I'll give you another solution to this in just a second. Maybe you were thinking of a different one. Limit as h goes to 0 of f of x plus h minus f of x all over h. And so here, we're saying this thing is x plus h. And we're saying this thing is f of x. And so this is f of x plus h minus f of x. And then if that's true, then h is equal to 0.2. And then we're saying, oh, the derivative at 1, plug in 1 to x cubed, and you get 1 out. And then we just solve. I'm going to keep that up there. The more standard way, perhaps, to solve this is what you do is you say, OK, well, the derivative is the slope of the tangent line. How about I just find the tangent line? I know the slope of the tangent line, and I know a point on the line, so that should be good enough, right? Do we know the point slope formula? So what we could do is we could say y is equal to, well, what's the slope at x equals 1? Or sorry, what's the slope at, what's the slope at x equals 1? It's 1 because you plug it into f prime. It's OK. Okay? So it's going to be 1 times, and then remember you do x minus, let's see, where we're going to be at 1. So x minus 2 plus the value at 1, which is 2. So this is equal to 1 minus 2 plus 2. Wait, I did something. Did I do something wrong? I did something wrong here. Yeah, this is supposed to be 1 here. I'm doing it all wrong. Everything here that's all wrong. There we go. Now this is going to be right now. X minus 1 plus 2 is equal to x minus 1. So this is the tangent line. And now we plug in 1.2 and, plus 1. So this at 1.2 is, what's 1.2 plus 1? 2.2. Does this seem like a big mystery what I was doing here? Where do I get the 1 from? This is the point slope formula where what you do is you do m times x minus x naught plus y naught. If you know a point on the line and you know the slope of the line, this gives you the formula for the line. You guys, do yourself a favor. We're going to ask you to give us tangent lines. I promise you. We're going to say, here's a function. Tell me the tangent line at y equals 2. If you just write it, if you compute the derivative, find the slope, put the points in here, leave it in this form, you are done. You understand me? This is the fastest way to do that problem. Just do it that way. Okay, so there's a picture in my mind, and I'm not sure if it's in everybody's mind, so I'm going to try to put this picture in everybody's mind. Well, that sounds weird. So now, here we go. This is the picture in my mind. I'm imagining, when I'm doing this problem, I'm imagining a curve that we can't see. And we're at x equals 1, right? So I labeled 1. And then here's going to be 1.2, right? And what do we know about our curve at 1? It's equal to 2. So here is 1, 2, 2. See, I'm writing with both hands. Ambidextrous. Not really. Okay. And now, do we know anything else? We don't know f of 1.2. There we go. But what do we know? We know the derivative, right? We know the derivative at this point, correct? And so the derivative is the formula for the slope of the tangent line. So I plug in this 1 into this formula. It gives me the slope of the tangent line. And then I compute the tangent line. And this gives me, see, an estimate for the value at 1.2. Sorry, my eyes just like glazed over. All right, so is it okay? That's what I'm doing over here. Does anybody see how these are connected? Nobody's saying anything. Yeah, sure, I'd love to. Okay, so green is my function. I'm going to start color coding everything if that's all right. Okay, so so this f of 1 equals 2. There's that f of 1 equals 2 right there. And then we say I want to approximate f of 1.2. So this is the value I'm approximating. But I don't know anything about it. I didn't give you enough information. All I say is approximate it somehow. Well, you know, I tell you that the slope of the tangent line is given by this formula, and the point we're interested in is 1. So we go here, and I say, hey, if you tell me that information, then you can find the formula for this line. This line here, this y, is my bright orange line there. That's what that is. That's that line right here. And so then I use the point slope formula to get x plus 1. It even kind of looks like, it looks exactly like x plus 1 actually. It's a miracle. And then I say at 1.2. So what you do is your approximation is up there. So you're not guaranteed to be spot on, but it's a good, this is what we found our approximation to be. Did that help at all? Okay, good. Good. All right, I have one more conceptual question, and then I have a bunch of computational questions. Oh, we got plenty to do on Monday too. All right, so here's my last conceptual question. And my phone is telling me that we are done. So I will do this last conceptual question. Here's one. I'm going to put it here on the front of the camera, and you watch the video. It'll be posted 4 weeks from now. And just read this. I'm just kidding, okay? So have a nice weekend, everybody.